Hi, in this video we are going to talk about shortest path algorithms, so let's get started. Basically, what is a shortest path algorithm? What is the problem itself? We would like to find a path between two vertices in the graph such that the sum of the weights of each edges is minimized. So for example, let's consider the fact that we would like to use Google Maps in order to get from a given city to another city. Basically, in the background, Google has a directed huge graph, and it's going to run the shortest path algorithm. It can be the Bellman-Ford algorithm, it can be Dijkstra algorithm, it can be A-star search, or it can be the Floyd-Warshall algorithm. But what's very important, then we can model the whole map of the world with the help of a directed graph. And basically, this is exactly what's happening behind Google Maps. So okay, the problem is that we would like to minimize the sum of the weights of the edges. And as I said earlier, there are several algorithms out there. Dijkstra's algorithm and Bellman-Ford are the most important ones. Okay, so what about Dijkstra algorithm? It was constructed by computer scientist Edgar Dijkstra in 1956. Dijkstra can handle positive edge weights only. It's very important. We are going to talk about Bellman-Ford algorithm that can handle negative edge weights as well. But as far as Dijkstra's algorithm is concerned, it is able to cope with positive edge weights. So the edge between two vertices must be greater than 0. There are several variants of the Dijkstra's algorithm. It can find the shortest path from A to B, but it is able to construct the shortest path tree as well. It defines the shortest path from a source to all the other nodes. So we are able to calculate the shortest path tree at once, and then we can reuse the shortest path tree from a given source. What's the disadvantage? That if the source has changed, for example, we have calculated how to get from Boston to New York, but if we are standing at Chicago, then we are not able to reuse this shortest path tree because the starting point has changed. So it's very important, then we are able to reuse this constructed shortest path tree, but if the source has changed, then of course we have to recalculate it. And this is asymptotically the fastest known single source shortest path algorithm for arbitrary directed graphs with unbounded non-negative weights. What about the time complexity? It is ortho v times log v plus e, where v denotes the number of vertices and the e stands for the number of edges in the graph. And basically, you may pose the question that, okay, why is it good to know data structures? Why is it good to know about heaps, priority queues, and so on? And basically for Dijkstra's algorithm, it's very, very important that without a proper data structure, the running time would be quadratic, v squared. But because we can use appropriate data structures such as Fibonacci heap or binary heap or priority queues in general, we could implement it with arrays, but whatsoever, we usually use heaps, binary heaps or Fibonacci heaps for Dijkstra's algorithm. We are able to boost up the algorithm and we are able to end up with a v log v, so linear arithmetic time complexity instead of the quadratic. And basically, linear arithmetic time complexity algorithms are the ones that can be used in practice. So if an algorithm has a quadratic running time, then it is not so efficient. We are not able to use it practically in softwares. Okay, so that's why proper data structures are very, very useful, because we are able to boost up, for example, Dijkstra shortest path algorithm, and we are able to end up with a linear arithmetic time complexity instead of the quadratic time complexity. Another important feature of Dijkstra's algorithm is that it is a greedy algorithm. It tries to find the global optimum with the help of local minimum, and fortunately, it turns out to be good. It's working fine. So it is greedy. On every iteration, we want to find the minimum distance to the next vertex possible. We are going to see a concrete illustration of how Dijkstra's algorithm works. It's going to be clear. And the appropriate data structures such as the heaps, the binary or the Fibonacci heaps, or in general priority queues, enable us to make sure that the running time will be as good as possible. Okay, and by the way, it is very easy to implement this greediness of the algorithm with the help of heaps, because basically we just have to insert the data to the heap and we just have to get the item, and if it's a minimum heap, it's going to return the minimum value. If it's a maximum heap, it's going to return the maximum value. Of course, in this case we have to use a minimum heap, so the minimum item will be the root node in the heap, because we are looking for a shortest path. If we would be looking for a longest path, of course we would have to use maximum heaps. Thanks for watching.